Hi everyone, let's do some drawing and talk about ATP synthase. So in the corner of our picture here, I've drawn a mitochondria, and you can see the components of the electron transport chain as well as the ATP synthase machine. So this ATP synthase machine is what we want to zoom in on and talk more about, recalling that the proton motive force, of course, is generated in this inner membrane space here, and that the ATP synthase machine taps into that, converting the pent-up battery-like force of the proton motive force into ATP through conversion to mechanical energy. So I want to zoom in on this ATP synthase machine, looking as though we could just make a huge blow-up of this region. So if we were to just draw a zoom in large and up close onto that. So we are working on drawing the F0, F1 ATP synthase. Interestingly enough, it got its name as F0 from the fact that the drug oligomyosin binds to and inhibits this complex. So why it turned into a 0 from an O, it's anyone's guess. But in any case, let's see if we can draw some of this phospholipid bilayer that we see there of the mitochondrial inner membrane on this zoom up. And then notice that we have a multitude of subunits within this large oligomer. So I'm just going to start drawing some of these subunits, and I'm actually going to begin with the C subunits. So depending upon whether you're looking at, say, E. coli or yeast, or whether you're looking at humans or plants, there may be anywhere between 10 and 14 C subunits. So these are the C subunits. I begin by drawing them because they are the turbine that turns when the proton motive force swooshes in. We additionally have the A subunit, and the A subunit is here. And I kind of did it in more fluorescent in this tiny drawing. We'll make it green. The A subunit, there's one of them. And then we have two B subunits. And I had made it bright pink. We'll make it the same here. So these B subunits, there are two of them, very elongated subunits. And you're noticing that these first subunits are all part of what we refer to as the stalk of the ATP synthase machine. So I'm just going to write that down. This is the F0 stalk. And really that's because it's the, this part that looks like it's rooted in the membrane. So that's the stalk. And then the other components, all in symbol font, are considered the F1 knob. So let's take a moment to draw the F1 knob. And we'll use some appropriately different colors. So the gamma subunit, arguably one of the most important components of the machine, it sticks down here. We had it in blue, and we'll label that as a gamma. And then there's also an epsilon subunit. Now, what is going to be true of both epsilon and gamma is that when the C subunits spin due to the proton motive force swishing in, they will allow the gamma and epsilon subunits to also spin, but the gamma subunit will spin inside of the catalytic subunits. So now to show the catalytic subunits, which are the alpha and beta subunits, I'm going to use another red here. And this is a bit hard to draw because, of course, that gamma subunit is inside of the catalytic subunits. So I'll use blue here for beta. And then another alpha. And there are actually 6 of these, so I'm able to sort of show you 3 here, and maybe we could kind of indicate behind here that we have more blues and one more red, perhaps. And get that sense. Now, the catalytic domain region here, as you might guess, the catalytic regions are in between 2 subunits. So when ATP, and I'll try to use a different color here, when ADP plus PI become ATP, this occurs at the interfaces between, so right here in between an alpha and a beta subunit, as best as I can show. Now we're missing just one additional subunit. You might have realized this connection between the B part of the stalk and the knob. So to add that in, is right here. And you might have guessed this is the delta subunit. So if I can get in there and write delta, maybe not my best effort. So then we should make sure we label alpha here and beta here, the catalytic subunits. Okay, so now we've kind of got this whole knob drawn, and we can remind ourselves of what's comprising the knob. So that's going to be made up of alpha 3, beta 3, gamma, epsilon, and delta. So that's all comprising that knob region there. And you can see the symbol font kind of designating that. Now, what happens is, remember our proton motive force here, all this pent up energy here in pumped protons that are in the inner membrane space. Well, when 3 protons swish in, we will see the kind of choppy, sort of spurt-filled rotation of the gamma, which then creates a change at the catalytic sites, and it's about 120-degree rotation that we see. So 3 protons come in, we get a 120-degree rotation. Now, this brings our attention to 2 different areas of the ATP synthase machine that we can give names to. So recognize that there is a rotor part of the machine. So we could say that the rotor, that is the part that spins, is the C subunits. It's the gamma subunit, and it's the epsilon subunit that all spin, whereas the stator, fittingly named, stays still. And so that is, of course, our A, our B, our delta, our alpha, and our beta subunits. They all stay in one position, but the spinning of the rotor creates the conformational change between the alpha and beta subunits that are so important to making ATP. Now, let's see if we could actually zoom, kind of look down onto this machine and see what's happening at each of the 3 catalytic sites. So pretend that you could either think about looking up or down so that you could see each of the catalytic sites between the subunits, the alpha and beta subunits, and that's what I'm going to try to draw on the next page. So if you think you're looking down, right, you're going to see these 3 catalytic sites between the interfaces. And I'm actually going to try to make them different colors. So in one catalytic site, we're going to see that it is called open. We're going to say that it's in an open conformation. So this site is going to be open. And at that site, ADP and PI are going to be binding. Now, the next site is going to be in the loose conformation. And at that site, we'll draw it like this. The loose site, we'll see that ADP and PI are bound. So in here, ADP plus PI. Now the next site, the third site, this is going to be the tight site. So at this site, ADP and PI are going to have formed that high energy bond, the phosphoanhydride bond, and this will have ATP. So this site is called a tight site. So now picture that 3 more protons swoosh in, another sort of clunky, chunky, jerky movement of the gamma subunit, and what was a loose site becomes a tight site. What was a tight site becomes an open site, right? And so we can see that, and in fact we could even go ahead and try to draw that. So let's give that a try. So saying that now that 120-degree rotation takes place, swishing in of 3 protons, now we can say that what was the open site now becomes a loose site. So let's start with our peace sign. Who says scientists don't have to know how to draw? You absolutely do. So this becomes a loose site, and now the ADP and PI are bound, and then what was a loose site, now that becomes a tight site. And now, of course, ATP has been made there. And then the tight site becomes an open site. Okay, so, and of course, what we can say there is that this ATP right here was released with, so there was 1 ATP made. Okay, and now then another 120-degree rotation, another 120-degree rotation. So for 360 degrees, we expect the synthesis of 3 ATP. Very cool. This is actually this idea that we are getting the movement of the rotor and the conversion of that to ATP synthesis. This is called the motor analogy. That makes a lot of sense, doesn't it? The motor analogy. And additionally, maybe just to mention, it wasn't all that long ago, in fact it was after I was born, that Paul Boyer in 1979 actually proposed this binding change mechanism is what we're actually looking at here. So this idea that we just looked at there, the binding change mechanism. This is awesome. So now we need to take a look back at our other picture, because check it out. We now have a bit of an issue, because note that the ATP that's all getting made is getting made inside of the mitochondrial matrix. So right here at the interfaces between these subunits, as we just saw, we get the ATP synthesized. But what if that ADP Or what if that ATP is needed out in the cytosol, where maybe it's going to power something like gluconeogenesis? And likewise, how does the ADP and PI, how do they get into the mitochondrion? So let's take a moment to look more deeply at that, and I'm going to draw another picture. This is a slightly larger zoom in to the mitochondrion, and we'll just go ahead and say that our ATP synthase machine is here. Now, I'm not going to get all colorful on you this time because you know a lot more now about the structure. You probably start drawing this in your sleep, I would guess. So there's that ATP synthase machine. There are worse things to do in your sleep, right? So we can now say we have a bit of a problem that there's ATP inside. How does the ATP get out? How does the ADP get in? And that's where another transporter comes into play. So in fact, there is a transporter that is called the adenine dinucleotide translocase, and I'm just making it all red here, the red box. The red box. It should be the name of a movie or something. So now we need to say that we need to get ADP in and ATP out. Well, conveniently, the adenine nucleotide translocase will take ADP 3- in exchange for, you guessed it, ATP 4-. Now you're probably wondering, why am I putting the charge of those molecules on there? Well, this is actually extremely important because notice what just happened there. A more negatively charged molecule went out and a less negatively charged molecule came in. So while you don't overtly see the charge for this transporter, notice that it is very much drawing upon delta psi. We can see the electrical potential has changed there because it has become less negative on the inside, drawing upon that delta psi. Now, likewise, let's take a look at the transporter that gets inorganic phosphate in, and it does so by taking a toll on the proton motive force. It's a symporter, so the H+, this is the H+ phosphate symporter. Now, this is a bit deceiving because, in fact, it's not the PO4 2- form of inorganic phosphate that comes in, but instead, or sorry, the PO4 3- version of phosphate that comes in. Instead, what happens is that H2 PO4- along with a proton swoosh into this symporter. So notice that this one has got a -1 charge and this one has a +1 charge, so there is no toll on the delta psi in this case. However, there is definitely a toll on the delta pH. So the delta pH is changing. Obviously, the pH is becoming slightly, slightly higher in the intermembrane space. So it is drawing on that delta pH. So overall, this toll that this cost, this charge of getting ADP in, ATP out, and getting inorganic phosphate in, there is a charge. The charge is approximately 1 proton. And so this is why we estimate 4 protons per ATP rather than just that 3 that we know has to come in through the ATP synthase machine in order to make an ATP. So we have to take into account the transport cost, if you will. I just briefly want to share with you this ribbon diagram structure of ATP synthase, and it was elucidated in 2009 and published by the von Bulmos et al. Group, and I'm sure I'm mispronouncing their name, but in any case, I thought this was a nice image to look at, and yes, I do know that it's upside down, but I wanted to show it the way that we're looking at it so that you see the catalytic subunits on the inner mitochondrial matrix region, and the C subunits, of course, spanning the membrane, and you can see how the proton motive force can pass through and turn those C subunits. Now,
I find that nearly every biochemistry textbook manages to somehow take the P to O ratio and make it into a far more complicated concept than it really is. True to form, right? So the P to O ratio, let's say what it means, and then let's talk about a simple way that we can think about it, or a simple way that we can express it. So P is going to stand for the molecules of ADP phosphorylated. So let me write this down. Molecules ADP phosphorylated. So the number of molecules of ADP phosphorylated could also be stated, right? If you think about this, ADP phosphorylated, what is made when ADP is phosphorylated? ATP, right? So we could also just simply say molecules of ATP. And this is a ratio to O, which that actually means the number of atoms of oxygen reduced. And that's an important differentiation. So the atoms of oxygen reduced. Okay, now that sounds pretty complicated. We know there's a link, right? We've been talking for a while about oxphos, so we know there's quite that link between oxidation and phosphorylation, the link made between the four members of the ETC and, of course, the ATP Synthase Machine that allows for that link to be complete. However, if we look at this, there's a bit simpler way to express all of this. If we say the number of molecules of ATP, that's a pretty good way to express it, pretty simple. Divided by the atoms of oxygen reduced. Well, do you guys remember what it took to reduce an atom of oxygen? I've gone ahead and drawn on the big picture view of the ETC. Horrible drawing, but it will do the trick. And if you remember at complex 4, 1/2 O2, which is one oxygen atom, right, is reduced to one water molecule with a pair of electrons that come from NADH. So that one pair of electrons, that is 2 electrons, that came from NADH led to the reduction of 1/2 O2, which is equivalent to 1 oxygen atom. So really, when we look back at this ratio, a simpler way to say this is the molecules of ATP per every one atom of oxygen is reduced with 2 electrons per 2 electrons. ATP per 2 electrons, right? Really, that's a much simpler way to think about this. Now, hang on though. You're telling me, Rachel, hello, those 2 electrons always aren't worth the same thing. 2 electrons from NADH are worth the pumping of 10 protons in complexes 1, 3, and 4. But what if those 2 electrons instead come from the oxidation of succinate? Right? Then they enter the chain lower on down, and they donate their 2 electrons to a non-proton pumping member of the chain, so they're only worth the 4 protons pumped here and the 2 here for a total of 6 protons. So you're right, it does depend on where those 2 electrons come from. It depends on whether they come from NADH or from QH2. So we're going to have 2 different P to O ratios. We're going to have the ATP per NADH ratio. Look how sweet that is. We just converted this weird looking sounding thing P to O to ATP per NADH versus ATP per QH2. And those two ratios are very easy to calculate. So that's our goal now, to calculate what sounds really hard, the P to O, by just simply calculating the number of ATP per 1 NADH and the number of ATP per QH2, something that you guys actually already know. I'm going to clear all out this mess and we're going to go on with that calculation then. Or for every one NADH that delivers its electrons to the electron transport chain, we remember that there are 10 protons pumped in complexes 1, 3, and 4, right? So 10 protons per 1 NADH. Now we know that it takes 4 protons to make an ATP. So let's set up our ratio so that we can cancel units, because that's just fun. So we remember it took 4 protons to make 1 ATP when we account for all of the needs for transport and whatnot. And when we go through the math here, we get something that looks pretty darn familiar to you guys. 10 divided by 4 is 2.5 ATP per NADH. You already knew that number. Now you see where we got it. 10 protons pumped for every pair of electrons that is donated by NADH. Takes 4 protons to make an ATP. So we end up with 2.5 ATPs per NADH, aka the P to O ratio for NADH. Okay? And then now we can do the same thing for QH2. Remember, it enters later, so only 6 protons are pumped in complexes 3 and 4. Per QH2 times 1 ATP per every 4 protons, and then that's going to equal our number that we already know, 1.5 ATP per QH2. So do you guys remember when I asked you to go ahead and do a quick calculation determining how many protons are pumped from the reducing power made in the TCA cycle? I want you now to take that calculation that you did for the number of protons that were pumped in the TCA cycle, and I want you to convert it now to the number of ATPs made. And you should come up with the same exact value that we got when we did this earlier during the chapter that we were talking about the TCA cycle. But do it this way so that you can see it happening as a conversion from protons. That'll be fun. Okay, let me know how it goes. So these calculated values then agree very closely with those observed experimentally when measuring the amount of oxygen reduced when a given amount of ADP is phosphorylated. So these ratios really are another way of saying the P to O ratio, ADP phosphorylated to oxygen reduced in terms of atoms of oxygen reduced, and that thus they're termed the P to O ratio.